This is a video from section 4.3. The directions say to find the local maximum and minimum values of f. And as a note, I'm going to apply the second derivative test for this video. All right, now let's take a look at example 1. Suppose I had f of x equals 2x cubed minus 9x squared plus 12x minus 3. So the first thing you want to do is you want to take the derivative. So we're going to look at f prime of x. So f prime of x is going to be 6x squared minus 18x plus 12. Remember, the derivative of x squared is 2x. The derivative of x is 1. Now, we want to find the critical numbers of f. So let's again copy this. So f prime of x is 6x squared minus 18x plus 12. So what we're going to do is we're going to set f prime of x equal to 0 to find the critical numbers of f. So we're going to take 6x squared minus 18x plus 12, and we're going to set it equal to 0. So if I divide everything by 6, what I get is x squared minus 3x plus 2 equals 0. So I'm going to factor, and I'm going to get x minus 1 times x minus 2 equals 0. So x is 1 or x is 2. And so what that says is the critical numbers are 1 and 2. Now, so what I'm going to do now is I'm going to take the second derivative. So I'm going to go back to that function there. So we know that f prime of x is 6x squared minus 18x plus 12. All right, let's look. Yep. Now, let's take the second derivative. So if I want f double prime of x, let's write that a little better. I get 12x minus 18. Now, I'm going to take these numbers and put them in for x inside the second derivative. So f double prime of 1 is 12 times 1 minus 18, and that's less than 0. And then f double prime of 2 is 12 times 2 minus 18, and that's positive. And so I'm going to tell you how I think about it. I think concave down. And over here, when f double prime is positive, I think concave up. And so when you're concave down, when the function's concave down, that means it dumps water. It looks like that's a maximum. And when it's concave up, that means it holds water. And that makes it a minimum. But I will give you formally what this means. Now, since f prime of 1 is 0, and f double prime of 1 is negative, right? Then f has a local max at f of 1, which is, now let's look. The original function is 2x cubed minus 9x squared plus 12x minus 3. So you're going to get 2 times 1 cubed minus 9 times 1 squared plus 12 times 1 minus 3. And so I'm going to get 2 minus 9 is negative 7. Negative 7 plus 12 is 5. 5 minus 3 is 2. And since f prime of 2 is 0 and f double prime of 2 is positive, then f has a local minimum at f of 2, which is 2 times 2 to the third minus 9 times 2 squared plus 12 times 2 minus 3, which is 16 minus 36 plus 24 minus 3. And so it looks like this is negative 20 plus 24 is 4. 4 minus 3 is 1. So f of 2 equals 1. And that's how you do the first example. If we look at example 2, we have this one. Suppose I had f of x, same directions, and I'm going to look at f of x equals e to the 2x plus e to the negative x. So if I look at f prime of x, I get 2e to the 2x minus e to the negative x. So I'm going to set f prime of x equal to 0. And so 2e to the 2x minus e to the negative x is 0. And so 2e to the 2x is equal to e to the negative x. And so I'm going to multiply both sides by e to the x. And so that says 2e to the 3x is 1. And so e to the 3x is 1/2. Okay? So from here to here, I multiply both sides by e to the x. Now, let's look at here. E to the 3x equals 1/2. So I'm going to take the natural log of both sides, and that's going to tell me that 3x is natural log of 1/2, which is negative natural log of 2. So if I solve for x, I get negative 1/3 natural log of 2. And so this is my critical value, my critical number. Okay? Now, the question is, what am I going to do from here? Well, let's go back to the first derivative. The first derivative is 2e to the 2x minus e to the negative x. So if I take the second derivative, I get f double prime of x is 4e to the 2x plus e to the negative x. So it's just chain rule. And what I'm going to do is I'm going to plug that critical value inside the second derivative. So let's again rewrite this. So f double prime of x is 4e to the 2x plus e to the negative x. So f double prime of negative 1/3 natural log of 2 is 4e to the negative 2/3 natural log of 2 plus e to the 1/3 natural log of 2. And so this is 4 times e to the ln 2 to the negative 2/3 plus e to the ln 2 to the 1/3. And so this is 4, this might be a little bit overboard, but you get 4 times 2 to the negative 2/3 plus 2 to the 1/3. And that's positive. If you can tell that it's positive from up here, that's fine. Exponentials are positive. They're never negative, okay? And they're not going to be 0. And so what that tells us is the following. And remember, when it's positive, before let's again stress, think concave up when the second derivative is positive. And since f prime of negative 1/3 natural log of 2 is 0, and f double prime of negative 1/3 natural log of 2 is also positive, what that says is f has a local maximum, not local maximum, concave up, so it's going to be local minimum at f of negative 1/3 natural log of 2, which is e to the 2 times negative 1/3 natural log of 2 plus e to the 1/3 natural log of 2. And this is e to the natural log of 2 raised to the negative 2/3 plus e to the natural log of 2, and then this is raised to the 1/3, and so this is 2 to the negative 2/3 plus 2 to the 1/3. And that would be your corresponding y value. And this would be one of those where you'd want to ask your instructor how far you want they want you to simplify. Okay, so that would be an instructor question as far as how far to proceed there. Let's do one more for this video, and we'll call this example 3. Suppose I give you this one. Now, f of x equals x squared ln x. Now, right off the get-go, we need to realize that x has to be positive, okay? Because you can't take natural log of 0. So when I look at the derivative, I take the derivative of the first, which is 2x, and I multiply by ln of x, and then I'm going to add x squared times 1 over x. So f prime of x is 2x ln x plus x. And I'm going to factor out an x, and I'm going to get 2 times natural log of x plus 1. So I'm going to set f prime of x equal to 0. And so what that says is x is 0, or natural log of x is equal to negative 1/2. And so basically I solved this one for natural log of x. And so x is 0, or x is e to the negative 1/2. But remember that x equals 0 doesn't make any sense, because in the original function, the domain here is from 0 to infinity. And so that is not a critical value. And so we can, right away, we can X that out. And so the only critical value that we're dealing with is e to the negative 1/2. Now, from here, I'll just use that. So we have f prime of x is 2x ln x plus x. So I'm going to take the second derivative, and I'm going to get 2 ln x, so I took the derivative of 2x, which is 2, times ln x, and I'm going to add 2x times 1 over x, and then I'm going to add 1. And so this is 2 ln x plus 3, and then I'm going to take the critical value, which is e to the negative a half, and I'm going to plug it in. So you get 2 natural log of e to the negative a half plus 3, which is 2. I could pull that negative a half out in front. And remember that natural log of e is 1, okay? So this is 2 times negative a half plus 3, and that's positive. So again, I think concave upward. And so since f prime of e to the negative a half is 0, and f double prime of e to the negative a half is positive, then f has a local minimum at f of e to the negative a half, which is, so let's go back to the function. Okay, so I'm going to plug e to the negative a half in there, right? So I'm going to get e to the negative a half to the second power times natural log of e to the negative a half. And so this is e to the negative 1 times negative a half, which is negative 1 over 2e. And that'll conclude this video for section 4.3. And we did 3 examples on essentially applying the second derivative test. So you notice here, anytime I get positive for the second derivative at the critical value, and f prime at that critical value is 0, we get a minimum. So that's what we did the whole time. Okay, and I hope that helped. So again, this is the second derivative test, 3 examples with different functions. Thank you.